SoundCheck features a multi-channel real-time spectrum analyzer, FFT spectrum analyzer, and oscilloscope integrated into the single multi-instrument. This lets you view any number of live waveforms simultaneously, and results can be time synchronized across the three instruments to simultaneously display parameters in both the time and frequency domain. Let's check it out. All three instruments can be opened from the instrument menu or with keyboard shortcuts, which opens them with their default settings. Let's open the FFT spectrum analyzer. On the left is the control panel, and next to it is the graph where the live curves are displayed. Live curves are also shown in the memory list and identified with a green dot. The multi-instrument graph is identified by its white shading around the plot area, but otherwise, it has the same functions as the standard graphs used in SoundCheck display steps. The acquisition controls are at the top of the control panel. The record and stop buttons are used to start and stop measurements, and when the instrument is in linear mode, the continue button resumes the previous linear measurement and continues until the start button is next used. The add button lets us add new instruments, calculations, graphs, and triggers to the multi-instrument. Let's use the FFT spectrum analyzer and look at some of the analysis options for stationary signals such as sine waves. I'm outputting a 1 kHz tone at 2 volts RMS from the signal generator. On the multi-instrument graph, we can clearly see the fundamental and the second and third harmonics. Let's drop a cursor on the fundamental using the snap to max function. Enable the harmonic cursor, and by exposing the advanced graph controls, we can get a real-time readout of the cursor frequency, level, and THD of the fundamental. Now, let's add a calculation. In this case, a real-time masking curve, which will show us how our dominant fundamental tone is masking other stationary signals. The masking curve suggests that all of the harmonics are below the threshold of hearing, but as we increase the signal level, they get closer to being audible. By adding a second signal generator, we can view intermodulation products. One generator is set to 340 Hz and the other is set to 7 kHz with a 4:1 amplitude ratio between the two signals. With these settings, we can clearly see the intermodulation products around the 7 kHz tone. I can save any virtual instrument configuration for later recall from the Instruments menu. Let's just close all to close all of my windows. And now I can reopen it without having to reopen and configure all of the individual instruments again. Let's switch over to a saved configuration with the RTA and signal generator and look at some of the other calculation options. The multi-instrument graph supports both live curves from the RTA and static curves from the memory list, and can use both in a calculation. Here, I'm sending a pink noise stimulus to the device under test, and I want to compare its RTA spectrum to a target response curve, which is already in the memory list. I can just drag the target curve over from the memory list to display it on the live graph. Now, I add a calculation for dB subtraction, where the live RTA curve is operand A, and the target curve from the memory list is operand B. This generates a real-time difference curve on my live graph, and I can name it something more descriptive. Another useful RTA calculation is power averaging. Let's add a couple of RTAs to the current configuration and assign each a unique microphone signal path. Notice how, when I add RTAs, they inherit the properties of the original RTA, so all I have to do is update the signal path assignment. Now I can add the power average calculation, select all three microphones, and we have the power average of the three microphones. Live curves can always be saved to the memory list by clicking the Save to Memory button. Once there, they can be displayed on other graphs or saved to disk. Other available calculations include maximum, minimum, and dB addition. Let's take a look at the oscilloscope. I'll open a saved virtual instrument that is configured with two oscilloscopes, monitoring two different input signal paths. The oscilloscope control panel lets us set the data name, signal path selection, time base, and measurement mode. The measuring indicator is bright green when the instrument is active and dark green when stopped. Now let's pause the signal generators and add a trigger. Our trigger level is set relative to the signal's peak level using either linear or logarithmic scaling. Slope selection lets the user decide whether the scope will trigger on the first positive or negative portion of the incoming signal, and offset allows you to determine the amount of time that the acquired signal is shifted relative to the point at which it is triggered. The trigger level is set to 300 millivolts on direct input 5. Let's start the signal generators and increase the signal level. Once we exceed the trigger threshold, we can see how the scope starts running. When the signal level goes below the trigger threshold, it stops. I hope you've learned a few things about the multi-instrument from this quick tip. Try it out for yourself and don't forget to check the user manual for more details.